Consider this number for a moment. 290 to 792, 458 meters per second. That's how fast light travels. Absurdly fast, incomprehensibly fast. The swiftest phenomenon in all of existence. Okay, we get it. Light is quick. But here's the question. Nobody really answers. Why can't anything surpass it? What's actually preventing you from going faster? The vast majority of people never genuinely interrogate this. They simply nod along. Einstein figured it out. The speed of light is nature's ultimate barrier. Case closed. End of discussion. But that's not explaining anything. That's just parroting a fact without comprehension. When you genuinely probe into what's blocking anything from exceeding light's velocity, when you actually investigate the mechanics of this prohibition, you stumble upon something so bizarre, so utterly alien to your daily intuitions, that it fundamentally reshapes your entire conception of reality. The speed of light isn't merely a velocity measurement. It's not simply the quickest phenomenon in existence. It represents the fundamental architecture of reality itself. It's embedded into the very essence of space and time in such a profound way that exceeding it isn't just difficult, it's conceptually incoherent. Allow me to demonstrate precisely what I'm talking about. We should begin with something elementary, something universally observed. Objects descend when released. Release any object, and it plummets downward. Galileo quantified this phenomenon centuries ago, approximately 16 feet of descent in the initial second of freefall. Release a sphere, release a stone, release virtually anything, and after precisely 1 second, it will have dropped roughly 16 feet. This seems straightforward enough. Gravity pulls things earthward. Simple. Now consider the moon hanging overhead. The moon circles our planet continuously. It doesn't plummet toward us. It maintains its position up there, perpetually tracing its orbital path, traveling in an enormous curve around Earth. But pause and reconsider this. Is the moon actually falling? Contemplate this scenario carefully. Suppose the moon were simply suspended motionless in space, completely stationary. What would occur? Gravity would drag it directly toward Earth. It would crash into our planet. But the moon possesses sideways motion. It travels perpendicular to the line connecting it to Earth. And because it maintains this lateral velocity while gravity simultaneously tugs it downward, it perpetually misses our planet. It descends toward Earth continuously, but never arrives. That's the essence of orbital mechanics. Perpetual falling combined with sufficient sideways speed to continuously miss the target. Here's where Newton achieved something genuinely extraordinary. The moon sits approximately 240,000 miles from Earth's center. Meanwhile, we're positioned on the surface, roughly 4,000 miles from that same center. Therefore, the moon occupies a position 60 times more distant than we do. Newton proposed a hypothesis. What if gravitational attraction diminishes with increasing distance? What if it obeys what we now term an inverse square relationship? This principle states that doubling your distance from a gravitational source makes gravity 4 times feebler. Triple the distance, and gravity becomes 9 times weaker. Multiply the distance by any factor, and gravity weakens by the square of that factor. If this hypothesis holds true, then at the moon's location, 60 times our distance from Earth's center, gravitational pull should be 60 squared times weaker. Calculate that out. 60 multiplied by 60 equals 3,600. Gravity at the moon's position should be 3,600 times feebler than what we experience standing on Earth's surface. Here on Earth, objects descend 16 feet during their first second of free fall. If lunar gravity is 3,600 times weaker, the Moon should fall toward Earth by 16 feet, divided by 3,600 every second. Work through that arithmetic. 16 feet divided by 3,600 yields approximately 1/20th of an inch per second squared. Let me express this more clearly. Accounting for the squared time relationship in gravitational acceleration formulas, we need to consider how far the Moon actually deviates from a straight-line path in 1 second. When Newton performed this calculation, determining how much the Moon should curve toward Earth per second if gravity followed his proposed inverse square relationship, the result aligned perfectly with astronomical observations. The Moon deviates from straight-line motion by exactly the amount Newton's mathematical framework predicted. This represented a monumental achievement. This wasn't merely theoretical speculation. This was predictive science in action. Newton extracted one completely independent observation, how rapidly objects fall at Earth's surface, and linked it to an entirely separate observation, the Moon's orbital period and its distance from Earth. Two phenomena that appeared utterly unrelated suddenly became unified through a single mathematical principle, the law of universal gravitation. There was no retreating from this insight. Physics had fundamentally changed. Newton pushed his analysis further. He mathematically derived what geometric shape planetary orbits should trace if gravitational attraction followed an inverse square law. His calculations revealed that orbits should form ellipses, stretched circles with the gravitating body at one focus. And what do we actually observe? Planets travel in elliptical paths around the Sun. Johannes Kepler had already documented this through painstaking astronomical measurements, but Kepler couldn't explain why ellipses specifically. He merely described the pattern. Newton provided the underlying mechanism. He derived 3 fundamental results from 2 basic principles. His explanatory framework was extraordinarily powerful. Additional phenomena suddenly became comprehensible. Consider oceanic tides. Why do coastlines experience regular tidal fluctuations? Because the Moon exerts gravitational pull on Earth's waters. But wait, if the Moon simply attracted everything earthward toward itself, we should observe only one daily high tide, correct? A bulge of ocean water on the hemisphere facing the Moon. Yet we observe 2 high tides approximately every 24 hours, occurring roughly 12 hours apart. Why would this be? Various explanations circulated. Some suggested Earth itself gets pulled away from the water on the far side. Others proposed that water simply gets drawn toward the Moon. Both contained partial truths, but neither captured the complete picture. Newton identified the actual mechanism. Gravitational force from the Moon acts on both Earth and its oceans. At any given distance, the attraction strength is identical. However, ocean water on the Moon-facing side sits closer to the Moon than Earth's center does. Therefore, this near-side water experiences slightly stronger attraction. Simultaneously, ocean water on the opposite hemisphere sits farther from the Moon than Earth's center. This far-side water experiences slightly weaker attraction. The result? 2 oceanic bulges form. One bulge where water gets pulled more strongly toward the Moon than Earth does. Another bulge where water gets left behind because Earth's center gets pulled more than that distant water. 2 tides daily, perfectly explained. There's an additional subtlety worth noting. Earth and Moon don't simply have the Moon orbiting Earth's center. Both bodies actually orbit their common center of mass, a point located within Earth but displaced from its center. You could conceptualize the far side tidal bulge as resulting from centrifugal effects in this rotating reference frame. Regardless of which perspective you adopt, the two daily tide phenomenon received complete explanation. Numerous other observations suddenly made sense. Why does Earth assume a spherical shape? Because gravity pulls all material toward the center. Why isn't Earth perfectly spherical? Because planetary rotation creates centrifugal effects that push equatorial regions slightly outward, producing an oblate shape. The bulge reaches equilibrium, where gravitational compression balances rotational expansion. Similar reasoning explains why the Sun, Moon, and other celestial bodies approximate spheres. As scientific methodology matured and measurement precision improved dramatically, tests of Newton's gravitational law became increasingly rigorous. Among the earliest high-precision tests involved Jupiter's 4 major satellites. Through meticulous observation of these moons' orbital motions over extended periods, astronomers could verify whether everything conformed precisely to Newtonian predictions. It turned out not to match. Jupiter's moons appeared to arrive at predicted positions sometimes 8 minutes early and sometimes 8 minutes late. 8 minutes represents a substantial discrepancy when your theoretical framework claims perfect predictive power. Something seemed fundamentally wrong. But then observers noticed a peculiar pattern. The moons ran ahead of schedule when Jupiter happened to be relatively close to Earth in its orbit. They fell behind schedule when Jupiter occupied the far side of its orbit, maximally distant from Earth. A strange correlation indeed. Ole Römer, maintaining confidence in gravitational theory, arrived at a remarkable conclusion. Light requires finite time to travel from Jupiter's moons to terrestrial observers. What we see when observing these moons isn't their current positions, it's where they were some time ago. The delay corresponds to how long their light took to reach us. When Jupiter sits nearby, light arrives more quickly. When Jupiter sits far away, light takes longer to arrive. Römer realized he could correct the observational data by accounting for light's travel time, and crucially by measuring how much, early or late, the moons appeared at various Earth-Jupiter distances. He could calculate light's velocity itself. This calculation produced the first scientific measurement of light's speed, determined not by directly timing light, but by trusting gravitational theory and explaining an apparent anomaly. This represented the first demonstration that light doesn't propagate instantaneously. Light takes measurable time to traverse distances. I emphasize this historical episode because it illustrates something profound about scientific methodology. When a physical law proves correct, it becomes a tool for discovering additional laws. By maintaining confidence in gravitational theory when anomalies appeared, Römer proposed that an additional phenomenon, finite light speed, might explain the discrepancy, and his proposal proved correct. Had we not possessed reliable gravitational theory, determining light's velocity would have required entirely different, potentially much more difficult approaches. We wouldn't have known what Jupiter's satellites should do, so we couldn't have identified the deviations pointing toward finite light speed. This exemplifies a pattern that has driven scientific progress exponentially. Each validated discovery provides tools enabling further discoveries. Each new understanding opens pathways to additional understanding. This cascade began with Newton's gravitational insights and has accelerated continuously for 4 centuries. We remain caught in this avalanche of expanding knowledge, progressing rapidly even today. Once the speed of light became measurable, once scientists could determine its value precisely, something extremely peculiar emerged. Light always propagates at identical speed. Universally, regardless of who performs the measurement, regardless of how the observer moves. Let me make this tangible with a concrete scenario. You stand motionless on solid ground. You activate a flashlight. You measure the velocity of the emitted light. Your instruments read 299,792,158 meters per second. Perfectly sensible result. Now you board an extraordinarily fast vehicle. Imagine a train capable of traveling at half the speed of light. While this train hurtles forward, you activate the same flashlight, pointing it in your direction of travel. Ordinary intuition suggests the light should now travel at light speed plus train speed. Just as throwing a ball forward from a moving vehicle makes the ball travel faster relative to the ground than if you threw it while stationary. That's not what occurs. You measure the light beam's velocity. Your instruments still read 299,792,458 meters per second, exactly identical to your stationary measurement. You assume your measurement contains errors, so you accelerate the train further. Now traveling at 90% of light speed, you activate your flashlight again, pointing forward. You measure. Still 458 meters per second. Growing increasingly frustrated, you push the train to 99.9999% of light speed. You fire your flashlight forward. You measure with utmost precision. The result, 219,792,458 meters per second. Unchanged, light's velocity doesn't compound with your velocity. It doesn't accumulate. It doesn't add. It remains absolutely constant regardless of your own motion. This observation should profoundly disturb your intuitions. This contradicts how velocities operate in everyday experience. Velocities compound. If you're aboard a train moving at 80 kilometers per hour and you walk forward through the carriage at 5 kilometers per hour, you're moving at 85 kilometers per hour relative to the platform. Speeds add together. But light refuses this behavior. Light always propagates at identical velocity relative to you, irrespective of your own speed through space. How can this be? Einstein recognized what this constancy actually implied. And the implication was so radical, so contrary to common sense, that even now, more than a century later, people struggle to internalize it genuinely. Space and time don't possess fixed, absolute properties. They're malleable. They warp and stretch, and they adjust specifically to maintain light's velocity as constant for all observers. When you move faster, time flows more slowly for you. Your clock genuinely ticks at a reduced rate. Simultaneously, lengths contract in your direction of motion. Space itself compresses along your trajectory. These effects are not illusions. They're not measurement artifacts. They're not tricks of perspective. Time actually decelerates. Space actually shrinks. And the magnitude of these distortions is precisely calibrated to ensure light's measured velocity remains identical for every observer in every reference frame. I want to emphasize this because it's so counterintuitive. The cosmos adjusts temporal and spatial properties, bending them, stretching them, compressing them, specifically to guarantee that light travels at the same speed for everyone. The speed of light isn't merely a velocity, it's a structural constant embedded in reality's foundation. Space and time are configured such that this speed remains invariant for all observers. Now consider what happens when you attempt to accelerate any object whatsoever, to light speed. Something deeply strange occurs. As you approach light speed more closely, further acceleration becomes progressively more difficult. This isn't because you've exhausted your fuel supply. This isn't because your propulsion system lacks sufficient power output. The object itself increasingly resists acceleration. We describe this phenomenon as relativistic inertia increase. As velocity increases, effective inertia increases correspondingly. Pushing the object faster becomes progressively harder. And as velocity approaches light speed, inertia approaches infinity. Actually reaching light speed would require infinite energy expenditure, an obvious impossibility. Therefore, nothing possessing mass can ever attain light speed, not due to arbitrary prohibition, not due to engineering constraints, but because space-time's fundamental structure forbids it. Photons, light particles, travel at light speed because photons possess zero mass. Massless entities can propagate at light speed. Indeed, they must. They have no alternative. They're perpetually moving at exactly that velocity. But any entity possessing mass, however minuscule, can approach light speed asymptotically. It can reach 99.9% of light speed. 99.9%. 99.9999%, but never quite attain it. Reality itself prevents that final achievement. You might now demand a deeper explanation. Why does the universe operate this way? Why does a cosmic speed limit exist at all? And here's the response that will likely frustrate you. There isn't a more fundamental why beyond what we've already discussed. The speed of light isn't an externally imposed restriction on the universe. It's a consequence of how the universe is fundamentally structured. Space and time aren't separate, independent entities. They're interwoven into a unified fabric we call space-time, and space-time possesses inherent geometry, inherent structure. That structure contains a built-in conversion factor relating spatial distances to temporal durations. That conversion factor is the speed of light. Light isn't special in itself. What's special is that space-time has a maximum rate at which causation can propagate. Light happens to travel at this rate because light lacks mass. But this maximum rate is a property of space-time itself, not a property specifically of light. Imagine light didn't exist at all. The speed limit would persist nonetheless. It's a fundamental feature of the universe's architecture. Here's an alternative conceptual framework that might help. In ordinary experience, you conceptualize space and time as distinct, independent things. You move through space. Time passes. These seem like separate phenomena. But they're not separate. You're perpetually moving through space-time at a constant rate. Always. Without exception. But your motion divides between spatial and temporal components. When you're stationary relative to some reference frame, all your motion is through time. You're advancing into the future at maximum rate. 1 second per second, as it were. But when you begin moving through space, you must divert some of your motion away from the time direction. You're now moving through both space and time, which necessarily means you're moving through time more slowly. The faster you move through space, the slower you move through time. There's a limit to this trade-off. If you could somehow move through space at the speed of light, you would have zero motion remaining for time. Time would completely halt from your perspective. This explains why light doesn't experience temporal passage. From a photon's perspective, emission and absorption are simultaneous events, no duration elapses. The universe is frozen in a single instant. You cannot exceed light speed because you cannot have negative motion through time. You cannot move backward through causality. That's the absolute boundary. That's the impenetrable wall. And here's what makes this beautiful. These aren't mere theoretical speculations. These predictions have been tested exhaustively, repeatedly, with extraordinary precision. particle accelerators routinely accelerate subatomic particles to 99.9999% of light speed. And consistently, without exception, further acceleration becomes progressively more difficult as particles approach the limit, exactly as relativistic theory predicts. Global Positioning System satellites must account for relativistic time dilation. These satellites move at significant velocities relative to Earth's surface, and they orbit in weaker gravitational fields than ground-based receivers experience. Consequently, time passes at different rates for satellites versus ground receivers. Without corrections for these relativistic effects, GPS positioning would accumulate errors of many kilometers within a single day. The corrections work perfectly, confirming relativistic predictions. Consider muons, unstable particles created when cosmic rays strike atmospheric molecules at high altitude. Muons possess extremely brief lifetimes. Their natural decay rate should cause them to disintegrate long before reaching Earth's surface. Yet we detect abundant muons at ground level. Why? These muons travel at velocities approaching light speed. Time dilation slows their decay rate from our perspective. Alternatively, from the muon's perspective, the distance they must travel is length contracted. Either viewpoint yields the same prediction. Far more muons reach ground level than classical physics would permit. And measurements confirm this precisely, exactly as relativistic theory predicts. This isn't speculation or philosophy. This is rigorously measured reality. Light speed's role as an absolute limit is among the most thoroughly tested propositions in all of physics. Let's consolidate everything we've explored. Why does the speed of light constitute an absolute limit? Because space-time is structured with an inherent maximum rate at which causation can propagate. That maximum rate equals the speed of light. Not because light possesses special properties, but because space-time itself contains this built-in relationship between spatial and temporal dimensions. You cannot exceed this limit because doing so would require backward motion through time, which is incoherent. You cannot achieve negative temporal passage. You cannot reverse causation. The speed of light represents the rate at which the present moment propagates through the cosmos. It's the maximum speed at which information can travel. It's the speed at which forces communicate. It's the ultimate rate of change. And this entire understanding emerged from a cascade of interconnected discoveries. Newton figured out gravitational mechanics by carefully analyzing the moon's orbital motion. Romer determined light's finite velocity by studying apparent timing anomalies in Jupiter's satellites. Maxwell unified electricity and magnetism and revealed that electromagnetic waves must travel at a specific velocity. Einstein recognized that this velocity's constancy demanded revolutionary reconceptualization of space and time. Countless subsequent experiments confirmed these theoretical frameworks with ever-increasing precision. Each discovery built upon previous ones. Each new insight opened doors to further insights. That's how scientific progress operates. That's the avalanche that's been accelerating for 4 centuries. And we're still riding that avalanche at tremendous speed right now, making new discoveries, testing new theories, pushing the boundaries of understanding. The speed of light isn't merely a numerical value in physics textbooks. It's a key that unlocks comprehension of how space and time actually function. It reveals that the universe is far stranger and more elegant than everyday intuition suggests. Consider what we've learned. Space and time aren't fixed, rigid backdrops against which physics unfolds. They're dynamic, flexible, responsive. They adjust to maintain fundamental symmetries. They warp in the presence of mass and energy. They're participants in physics, not merely stages. The cosmos has built-in structure that determines what's physically possible. That structure includes a maximum information propagation rate. That rate happens to be the speed at which massless entities travel. We call it the speed of light because light was the first massless phenomenon we studied in detail. But it could equally well be called the speed of causality or the space-time conversion constant. Understanding why light speed constitutes an absolute limit isn't merely academic curiosity. It has practical consequences and philosophical implications. Practically every modern technology involving precise timing or rapid communication must account for relativistic effects. GPS navigation, particle accelerator operation, satellite communication synchronization, all require relativistic corrections. Our technological civilization depends on understanding these phenomena. Philosophically, recognizing that space and time aren't absolute, that they're malleable, observer-dependent, interconnected, fundamentally changes how we conceptualize existence. Simultaneity isn't absolute. Two events occurring at the same time for one observer might occur at different times for another observer moving differently. The present moment isn't universally shared. Each observer has their own present, their own past, their own future. This doesn't make reality arbitrary or subjective. Physical laws remain identical for all observers. Measured quantities transform in predictable, mathematically precise ways between reference frames. But the naive notion of a universal now, a cosmic present moment shared by everyone everywhere, turns out to be incorrect. Physics continues advancing. We now understand that gravity itself is space-time curvature. Mass and energy don't just exist within space-time, they shape space-time's geometry. We've detected gravitational waves, ripples in space-time propagating at light speed, just as relativity predicted. We've confirmed time dilation, with atomic clocks flown on aircraft, and with particles in accelerators and with satellites in orbit. And still, there are mysteries. Quantum mechanics and relativity don't fit together seamlessly. We lack a complete quantum theory of gravity. Dark matter and dark energy, which apparently constitute most of the universe's contents, remain poorly understood. The avalanche of discovery continues, but the speed of light remains central. It's the cosmic conversion factor. It's the bridge between space and time. It appears in virtually every fundamental physics equation. E equals mc squared. That's the speed of light linking mass and energy. Every electromagnetic phenomenon propagates at this speed. Gravitational influences propagate at this speed. Information cannot exceed this speed. So when someone asks, why can't anything go faster than light? You now possess genuine understanding, not just a memorized phrase. The speed of light isn't an arbitrary speed limit imposed from outside. It's intrinsic to space-time's structure. Space and time are interwoven with this particular conversion factor built in. Exceeding it would require negative motion through time, which is meaningless. Nothing with mass can reach light speed because doing so would require infinite energy. Inertia increases without bound as velocity approaches that limit. Massless things travel at exactly light speed, always, because that's what massless propagation means in our space-time geometry. The universe isn't preventing you from going faster through some prohibition or barrier. Rather, faster than light doesn't correspond to any physically realizable state. It's like asking to go north of the North Pole. The question itself is malformed. And this is what makes physics beautiful. Not comfort, not simplicity, not intuitive satisfaction. Truth. The universe operates according to principles that can be discovered, tested, verified. Those principles often violate naive expectations. They often demand conceptual restructuring. They often reveal that reality is stranger than fiction. But they can be understood. A human brain, evolved for navigating African savannas and social politics, can grasp the fundamental architecture of space-time, can comprehend why nothing exceeds light speed, can derive equations predicting how time dilates and space contracts, can verify those predictions through ingenious experiments. We're small creatures on a small planet orbiting an ordinary star in an unremarkable galaxy, yet we've figured out that space and time are unified, that mass curves space-time, that there's a cosmic speed limit woven into reality's fabric. We've measured that limit to 9 significant figures. We've confirmed its consequences through countless experiments. The speed of light, 299,792,458 meters per second, isn't just a number. It's a window into the deep structure of existence. It's a clue that revealed space and time aren't what they seemed. It's the thread that, when pulled, unraveled our naive conception of reality and revealed something far more intricate and beautiful beneath. That's the story of the speed of light. That's why nothing can go faster. And that's why understanding this matters, not just for physics, but for appreciating how magnificently strange and comprehensible our universe actually is. The avalanche of discovery that began with Newton watching apples fall and moons orbit continues today. Every new experiment, every new observation, every new theoretical insight builds on everything that came before. And at the center of so much of it sits this peculiar constant, the speed of light, connecting space to time, linking mass to energy, establishing the cosmic tempo at which cause becomes effect. We're still avalanching along at high speed. And the view from here is extraordinary.